In this video, we're going to be talking about the basics of decision theory. What is decision theory? Decision theory is the study of reasonable decision-making in contexts that vary with respect to the knowledge available. And here, when we talk about a decision, we're talking about a decision to take some action. The goal of decision theory is to develop criteria for rational, that is, for reasonable, decision-making. This often involves maximizing utility. The term utility, as we'll be using it here, refers to desirability, positive utility, or undesirability, negative utility of a situation. Utility in this sort of sense gets used in a lot of contexts. Economics is a popular one. If this definition is slightly different than the one you may have gotten elsewhere, that's okay. For our purposes, broadly understood, utility refers to desirability or undesirability of a situation. Thus, when contemplating an action that could result in a prison sentence, for example, the negative utility of serving time in prison, the undesirability of that, should be considered along with the probability of serving time. And what we're going to see is that it's utility and probability. These are the two factors, the two variables that we'll be working with in doing decision theory. We're going to look at three general contexts under which decisions occur. The reason we make the divide into these three different contexts is because the decision procedures are a little different under each. So the first category, decisions under certainty. This is context in which the relevant state of the world is assured. Second, we've got decisions under risk, context in which we can assign probabilities to states of the world that we believe are relevant to our actions. And then third, we've got decisions under uncertainty, context in which various relevant states of the world are possible but of unknown probability. So the difference between Category 2 and Category 3, in both cases where we don't know what's going to happen, we can assign probabilities to the likelihood of outcomes in decisions under risk, whereas we aren't doing that or can't do that with decisions under uncertainty. We're going to look at each three of these kinds. We're actually going to start with number 2. It's perhaps the most paradigmatic sort of example of decision theory, which works as a good start. So, decisions under risk. In dealing with decisions under risk, the two variables you are keeping track of are 1, the probability that a certain outcome will occur, and 2, the utility of each of the possible outcomes. So we've got probability of an outcome as one variable, and utility of each of the possible outcomes as the second. To think about decisions under risk, imagine this situation. This is from your book. That you have hearing loss in one ear, and your doctor believes if you undergo an operation, there's a really good chance that you can dramatically improve your hearing in that ear. But there's a small chance you might result in further hearing loss. More specifically, your doctor thinks if you have the operation, there's an 85% chance that your hearing will drastically improve in that ear. And because, as we learned in the last lecture, when we're doing probability theory, percentages are represented between 0 and 1. This 85% chance gets represented as 0.85. Your doctor also thinks, there's maybe a 10% chance, roughly, that there won't be any change at all. And she thinks there is this 5% chance that you can, in fact, damage your hearing more if you have the operation. And of course, if you refuse the operation, well, there's not going to be any change. That's more or less certain. Perhaps exactly perfectly 1 is too high. A miracle could occur. But for the sake of our kind of frictionless scenario where we're looking at ideal working conditions for decision theory, we go ahead and use 1 for practical certainty, which means the options of improvement or further damage if you don't have the operation are practically 0. So what this models for us is the probabilities. We now have a look at, hey, look, what's the probability of each outcome if you go ahead and have the surgery? And what's the probability of each outcome if you refuse the surgery? So we've got probabilities here, but what do we want to say about utilities? Because to correctly evaluate decisions under risk, we need a rule that will account for both the utilities and probabilities of the options. Well, we'll come back to exactly how to lay out something like this for utilities in a bit. For now, let's start by looking at this maxim. Choose an action that maximizes expected utility. That's one such rule that you can use in trying to decide what to do in a decision under risk. To understand the rule of maximizing expected utility, we need to know how to calculate expected utilities. This requires us to quantify or measure utilities, something we'll come back to in a minute with the ear case, but it's something we're going to start with in the following example. And the reason why we're starting with this example is this example deals with money, and transferring units of currency to units of utility is a lot more straightforward. Okay, so imagine this situation, also taken from your book. You're at a fundraiser for your school library, and there's a bunch of games you can play. You're trying to decide between playing a punch board game or a game in which you throw dice. Info about the punch board game. It's going to cost you $2 to play it, and there are 4 possible outcomes. You can win $10, you can win $5, you can win $2, or you can win nothing. This seems like, hey, a pretty good setup when you just look at the 4 options. But then, of course, we've got to look at the probabilities. You only have a 5% chance of winning the $10. You've got a 10% chance of winning 5, a 20% chance of winning 2, and a whopping 65% chance that you aren't going to win anything. So that's the situation for the punch board. Then this is the info we have about the dice game. It will also cost you $2 to play, just like the punch board. So what you're putting out there, what's at stake, is the same in both cases, $2. There's 2 dice in the game, and if you roll a matching pair, you win $10. If you roll anything other than a matching pair, you win nothing. Okay. In general, the rule for calculating the expected utility of some decision is to multiply the probability of each relevant state of affairs by the total units of utility associated with that state. The sum of these products minus the initial costs, also measured in units of utility, if any, is the expected utility of that decision. If you have trouble tracking what exactly that looks like when written out like this, don't worry. We're going to look at some examples. Namely, the examples we've already started. Okay, so the expected utility of a $2 punch in this game for the library fundraiser can be calculated by letting each dollar equal to 1 unit of utility. So that's our conversion rate. $1 equals 1 unit of utility. You could come up with a more complex conversion rate and still compare the options, this option with the dice game, but there's really no reason to do something more complex when this will do just fine. Then we're going to multiply each payoff with its associated probability, then sum the results and subtract the cost of playing the game. So what we're doing is what this says we ought to do. So remember the first option was, hey, you could win $10, and there was a 5% chance of that. So converting the $10 to 10 units of utility, we've got 10 times 0.05. Then we're going to add to that the fact that there's the option of you winning $5, and there's a 10% chance of that. The fact that you could win $2 and a 20% chance of that, and the fact that you could win nothing, and a 65% chance of that. And then, of course, we have to subtract out the initial cost of playing the game, the $2. If we don't factor in the cost, it should look like, hey, you ought to play this punch game forever because this number is going to be greater than 0. But that's because we forgot to take into account the cost, the $2. So, multiplying these 4, we get 0.5 plus 0.5 plus 0.4 plus 0 minus 2, which gives us negative 0.6. So that's our expected utility for playing the punch game, negative 0.6. Okay, now let's take a look at the dice. For the dice game, once again, we'll set $1 equal to 1 unit of utility. There's a 1/6 chance of rolling each die with a matching number. And if that happens, you win the $10. That means there's a 5/6 chance that you won't, and you'll win nothing. Thus, we can calculate the expected utility as follows. So you've got 10 times this 1/6 plus 0 times this 5/6 minus 2, which is our initial cost. These turn out to be 1.67 and 0 and 2, which gives us negative 0.33. So if your goal is to maximize expected utilities, you ought to play the dice game, which is only negative 0.33, as opposed to negative 6. It's negative 0.6. You might be thinking, maybe I just won't play anything, but come on, it's a library fundraiser. Don't be a jerk. Okay, now let's go back to our hearing situation. Remember we had the probabilities outlined for us like this. And the question was, what do we do with utilities? There's not an obvious answer here like there is with dollars, which can just be transferred from one kind of unit to another. So basically what you have to do in situations where you're dealing with utility that isn't easily quantifiable is just kind of think to yourself, what would be an accurate representation of the value I'd attach to the different options? Okay, so here's one way you could assign values. Let's say you're pretty interested in your hearing being improved to very good in this ear, so you go ahead and assign 10 units of utility to that option. This over here indicates the probability. This is just a reminder for us of what the probabilities are along with the utility. Let's say if you decide to have the operation and it results in no improvement, you give that a utility of negative 2. Why negative 2 and not 0? Well, you went through the hassle of having an operation and it didn't do anything for you. So negative 2. And there's a 0.1 chance of that. Further damage, that sounds pretty bad. Not only have you undergone an operation, you've further damaged your hearing. We're going to give that a negative 10, but there's this low probability it'll happen. If you decide not to have the operation, well, there's no change. You're not really benefited or harmed, so the utility is 0. Now, using the rule we set out before, we can take the three options, this 0.85 chance of improvement and the 10 units of utility that would give you, multiply that, add that to the 0.1 chance that there'd be no improvement, and multiply that by the negative utility, and then the 0.5 chance that there would be damage, and multiply that by the negative utility. And that gives you 7.8, whereas the expected utility is 0. So here, at least, if the utility assignments you gave are somewhat reflective accurately of your actual preferences, it seems like a pretty clear decision to go ahead and have the surgery. Alright, so that's decisions under risk. Let's take a look very quickly at decisions under certainty. Decisions under certainty occur when you can be reasonably certain what the outcome will be of any decision you make regarding a matter. Now, we say reasonably certain because a lot of times, there's weird outside chances things could go wrong. If you're trying to decide whether or not to stay home or go to the park, it's theoretically possible that a meteor could hit the park before you get there, so there wouldn't be a park anymore and you couldn't go. But we're not going to worry about far out possibilities like that. If you can be reasonably certain if you decide to go to the park, you'll make it to the park. Reasonably certain if you decide to stay home, you'll stay home. That's good enough for our purposes to categorize something as practically a decision under certainty. As a result, because you know what the outcomes are going to be if you make particular decisions to act certain ways, you don't need to calculate the probability of different outcomes. So the focus is on utility. There are some interesting things that can be done with decisions under certainty. Your book talks a little bit about it, but we're not going to go into it. Alright, so let's turn to decisions under uncertainty. In a decision under uncertainty, you not only don't know what the outcome for different decisions will be, as you do with decisions under certainty, you also don't know the probability of how likely the different outcomes are, as you do with decisions under risk. As a result, you cannot use the same calculation of probability and utility that we use with decisions under risk. What you can do is rank order your preferences based on activities and outcomes. So in this particular example, your preferred outcome would be if you did action B and got the second outcome. After that, you'd like to do action B with the first outcome. After that, action A with the second outcome, and action A with the first outcome would be your least favorite way for things to go. So something you might notice about this example, in both cases with action B, take an outcome, the preference is higher on action B than it is on action A. For this reason, action B is said to dominate action A, because given any outcome, action B ranks higher than action A relative to that outcome. And in this case, actually just relative to anything in general. So assuming which outcome one chooses doesn't impact the probabilities, action B is clearly going to be the rational decision to take in this situation. And that's the way it usually works when one decision dominates another. But now let's look at this scenario. On this case, looking at outcome 1, action A gives us the better outcome than action B, but looking at outcome 2, action B gives us the better outcome than action A. As a result, neither action dominates the other. You might employ the method of seeing if either action guarantees a satisfactory action. That is, an action that is associated with that is not associated with any unacceptable state of affairs. So let's say, for example, you're like, okay, I'd be cool with outcome 1, outcome 2, or outcome 3, but not state of affairs 4 over here. Well, in that case, you ought to go with action B because there's only acceptable options, 1, 2, and 3. If you were only going to consider 1 or 2 acceptable, well, then you'd be in trouble because you can't guarantee a satisfactory action. A lot of times when it comes to decisions with uncertainty, which course of action you choose depends on your goals or your decision-making style. Your book identifies different types of decision-making personalities. First, they've got the gambler, someone who is apt to take the risk to try to go for the best possible outcome, even if the best doesn't happen. It's a pretty unsatisfying alternative. Then you've got the cautious player, the person who tries to avoid the worst situation. So even if they are willing to sacrifice the best, so long as they avoid the worst, that's what they'll go for. And the calculator, someone who tries to find the highest average utility. You can't work probabilities into account, but you can say, okay, given each outcome, if you treat it equally probably, what would happen? So there's that. Well, that's all we're going to cover in the videos from Chapter 6. Your chapter also talks about the prisoner's dilemma, the St. Petersburg paradox, and the gambler's fallacy. What I've included in the description for this video are other videos made by other people about the prisoner's dilemma and gambler's fallacy, so I would recommend checking those out if you want some kind of supplementation to what was covered about these topics in your book. Alright. That is all for Chapter 6. Next week, we move on to Chapter 7.